Good afternoon, everyone. Today we have Shotaro talking about his research. Shotaro got his PhD in high energy transient astrophysical phenomena, such as FRB and magnetic flares in Tokyo, in University of Tokyo. And after that, he went to Hebrew University in Israel for his first postdoc, and he just arrived Taiwan National Junction University, working with Tetsuya Hashimoto earlier this year, I think February. Yeah. Yep. He's now working on high energy transient phenomena, including FRBs and GRBs. And let's welcome him.
Thank you, Ida, for introduction invitation. So thank you everyone for joining today. I'm Shotaro. Today I will talk about my research on mostly related to Magnetar physics. Actually, I'm focusing on transient activity of Magnetar, which could be sometimes X-ray flare, sometimes maybe radio flare. So this kind of transient activity could be proved by considering what's going on actually near the star. Especially I'm focused on the plasma creation near the star. So I'm welcome to be interrupted anytime. So if you have any minor or major question, you can stop me. So thank you. Okay. So today's topic, I have 3 topics to be talked. First, I talk about magnetosphere spectra. And also we have a radio pulsation, like normal pulsar pulsating neutron star from Magnetar, and also this Magnetar flares in other wavelengths. So I will talk about the connection, potential connection between them. And also finally, I talk about recent, maybe one of the most astonishing phenomena discovered in our galaxy. Actually, fast radio burst is discovered in our galaxy, and also this fast radio burst is localized to the one galactic magnetar. So now we have a more convincing evidence for their connections. So I talk about these 3 topics, hopefully. So the first introduction. So of course, most of you know the radio pulsar. Now we know it is a rotating neutron star. This neutron star has relatively high magnetic field, and I think that this is the very famous picture of the pulse. So this is the time, and this is the rotational phase. So each time that we see some radio pulse, and how this is observed depends on the geometry and also the geometry of the viewing angle. So neutron star has 2 magnetic poles, and along each pole, particle is accelerated, and this emission is observed as a radio emission. And of course, the neutron star is rotating. The axis is different from the magnetic axis often. So we see periodically see this pulsation. So this is the general picture of radio pulsar. So this is the normal neutron star. Okay, so then what is the magnetar? So magnetar is neutron star that especially with strong magnetic field. So this is the plane often used in the pulsar community. The x-axis is the period of the rotational period, and the y-axis is the period derivative. Actually, they emit energy through radiation every time of rotation. So they lose that. So period increases as time goes. So this is a typical distribution of radio pulsar. So of course discovered by radio observation. Then magnetar population is around here. So they are clearly at different location on this phase space. And more interestingly, if we put the magnetic field strength, then this is the critical, so-called critical magnetic field strength, about which quantum effect becomes more important. So most magnetar has a surface magnetic field of about 10 to the 13 Gauss. So this is crazily high value. So this discriminate in a sense between normal radio pulsar and magnetars. And more, so first of all, Magnetar is not discovered in radio. It is discovered by X-ray or gamma ray observation because they are discovered as a flare. So this flare doesn't occur periodically. So this flare happens occasionally from somewhere in the galactic plane. So we see, of course, in gamma ray telescope, then we discover Magnetar, and then after that we observe in radio or other wavelengths to confirm the periodicity. So this is a completely different way to discover. So these two populations are discovered differently and also occupying a completely different phase space. Sure.
Can I ask about what's the story about
sure.
this, the one with the upper limit,
yes.
the Magnetar?
Upper limit? We don't know, but so far the highest surface magnetic field strength is about 10 to the 15 Gauss.
Right, I mean this red data points on the right,
yeah,
which is below the critical one.
Yeah, below.
The two red data points there.
Okay. So these are also discovered by bursting activity, but somehow they have a relatively low magnetic field. So this is actually a very good question. This is related to my second talk.
Okay.
So actually the criteria between Magnetar and radio pulsar is now not so clear. Yes, so that's a very important point actually. Thank you. So how Magnetar is discovered is through the bursting activity. So this is called Magnetar flare or Magnetar burst. And this has a pretty long history of observation. And actually they have so many different kinds of bursts. Most common burst is called short burst. Why short is the duration? Duration is very short, around 0.1 to 1 second. And the energy, luminosity is relatively low. Of course, this is so energetic compared to the normal Magnetar surface luminosity. This is the normal Magnetar surface X-ray luminosity. So around the time of burst, this increases more than 4 or 5 order of magnitude. So this is super bright. Then we can discover Magnetar. This has a typically thermal spectrum around KED. Then very rare event, but most interesting event is the giant flare. Actually, this as the name tells, it is so bright, so much brighter than this flare. And this actually one of them was the brightest gamma ray event that human ever discovered. So this occurs around 2004, I remember. Then this is a bit different population, but the energy continues around 10 to the 39 to 10 to the 47 L per second. So this is, if you write this event rate as a function of energy, this continues over more than 8 order magnitude in energy. And this is typically, distribution is power law. So we see the same population of single phenomena. So this is the quick summary. And this is the actual observation of some giant flare. And actually you see this crazy first spike. Then you see this kind of periodic, quasi-periodic modulation. And actually this modulation period is corresponding to the rotation of the neutron star, which is about 5 seconds or so. So it is not fast rotating, it's very slowly rotating. So these are the very famous example. So the next question is, what produces this? So most famous theory is for Magnetar flare phenomena is the creation of the fireball. Fireball is the product of magnetic energy release when the magnetic energy is released inside the magnetosphere, where magnetic field is super strong. It immediately creates a population of pair plasma, electron-positron pair plasma, and this is also connected with the gamma ray because they create each other. So this is kind of proof of pair plasma and also gamma ray. So this is super optically thick. So we only see the thermal emission from the surface. This is about gamma ray energy. And this is somehow confined near the star. because the magnetic pressure surrounding this is very strong. So this cannot normally expand freely. So once this is created, this is on the star, and the star is rotating. So we see some kind of periodic modulation in the resulting flare. So this is the very classic picture of Magnetar flare. Of course, we don't know much about the detail, but this is a very rough picture. And the number density here is so high, super high. So typically, this kind of crazy number density is maintained. And this is determined by the just the temperature of the fireball. So of course, if the energy release is so high, maybe some plasma is outflowing. So we see also a wind-like component, which might emit maybe non-thermal emission. But we don't know yet. So this is very important in my talk, so please remember. Then I move to the first topic. So how the spectrum of Magnetar flare is observed and how it looks. So this is also our introduction, but this is the actual spectrum of Magnetar flare from this Magnetar in 2001. This is pretty bright Magnetar flare. And the data point is from soft X-ray to hard X-ray here. And typically, theoretically, emission should be thermal emission, black body emission, because the fireball is super optically thick. So the photon escaping from the fireball is already thermalized. So this is the theoretical line here. However, we see clear discrepancy here between observation and theory at maybe hard X-ray range, about 20-30 keV. So this has been a long standing problem for maybe 20 years. So I consider what produces this. Then one important process inside the magnetosphere. Magnetosphere is the surrounding environment surrounding magnetar. So this is called magnetosphere. And in this work, I focus on the resonance cyclotron scattering. So this scattering process I will explain. So please imagine this is a magnetosphere, and there is a dipole magnetic field line here, and you have one electron or positron. Initially, this kind of particle is kind of doing the gyro motion around the magnetic field and emitting synchrotron emission. Then they lose their energy of which is parallel to their this direction. So this kind of parallel momentum is quickly lost because magnetic field is super high. So this time scale is almost instantaneous. So they cannot move. They can move only along the field line. Okay, then this electron, if there is some light emission from the neutron star, this emission, actually there is an important quantity here, cyclotron energy, which is determined by the magnetic field. And if electron is encountered with the light, which has exactly the cyclotron frequency, then this electron will absorb this photon, then emit this photon to the random direction with the same energy. So this is called resonance cyclotron scattering. So this is resonance process only happening at this energy. And so this is kind of inverse Compton scattering because the resulting emission is affected by the motion of the electron. If the electron is moving highly relativistic, the resulting emission we observe in the observer frame is different. So this process could be responsible for the Magnetar flare spectrum. So, okay, so this is the magnetar, and this is the surface. If the flare occurs, there is a fireball here, and the fireball is emitting, roughly speaking, 10 order of 10 keV rapid. Okay. Then, because dipole field has a magnetic field depends on the radius from the star. So this is the dependence. So it actually quickly fades if you go far, if you are far from the star. So at some point, this energy is proportional to the magnetic field, and this energy is becomes the same as this energy. Right? So light travel, and there should be a scattering layer where this scattering process happens. So this process is inevitable in magnetosphere. So any emission from the surface of the neutron star will experience this process. So this is very kind of trivial, almost trivial things. So let's think about it more carefully. So this is a picture. So let's assume fireball formation, and we have some photon, and we have assumed the dipole field, which is okay, globally okay, and then this photon experiences scattering. So what we don't know about the magnetic field, so we know about the magnetic field structure, but we don't know about the velocity field, how fast electron is moving. We don't really need to know this. So, but this could be obtained by a very easy kind of thought experiment. So this is the picture in the electron rest frame. The electron is not moving, and this is a magnetic field. So actually, this is the, okay, let's assume. So this is the angle of angle between the emission and the electron moving direction. So this is the rest frame. So using the very easy kind of special relativity, you can translate this rest frame quantity to the observer frame quantity, and also this is electron velocity in unit of light. So please look at this equation. Okay, let's assume first, initially, the electron is not moving very fast. So this delta E is close to 0. Then this numerator, this is some positive value between 0 to 1. This numerator itself becomes positive. This means the left-hand side, cos theta, becomes positive. This means this theta should be smaller than 90 degrees. This means the direction of the radiation force is pushing this electron in the electron rest frame. So electron will accelerate by this. However, once this beta is larger enough, then this numerator, this becomes negative. Right? So beta is larger than cos theta. This is happening actually. Then left-hand side, this becomes positive. No, negative, sorry. This is negative and negative. Then this means the direction of the radiation force is now kind of backwards. So electron gets some feedback in terms of velocity. So this kind of experiment, you can do this inside your head. And then this immediately tells that there is an equilibrium state which dictates the velocity of electron. Actually, this should be 0, always 0. Because the force is so strong. So force is always acting perpendicularly to the electron direction. So once you have this, if we determine the direction of the photon, we know the velocity of electron on the magnetic field. So this tells you the velocity distribution. And also importantly, because this quantity is less than 1, right? So also the Lorentz factor is like this. So this cannot be larger than like 100 or 1000. So this tells you electron is not moving relativistically. It moves relatively slowly. So this is important implication. Okay, so then we know the magnetic field geometry and also the velocity of electrons. So we can actually calculate how spectrum is affected by this process. So I consider a simple toy model, just considering this kind of geometry. Neutron star rotation axis and the magnetic field axis is the same. And this is the fireball as a point source. Radiation is scattered here. So the one important parameter is the fireball temperature. So I need to determine the fireball temperature as a free parameter. Then we can calculate a single scattering process. So this can be done by a Monte Carlo method. Okay, let's see the result. So this is the case of if we are injecting single energy photon, like 10 keV, then this photon distribution is kind of expanded here. Like this kind, you can see this extended distribution by this process. Actually, the upscattering in energy is not that large. It's only about a factor of a few, actually 2. So this is a very small shift, but actually important. So next step, we can do this actually using the fireball spectrum. So the original fireball spectrum is this gray curve. This is a black hole spectrum. And then this will be slightly modified like this. So this shift is also about 2 times. And this doesn't strongly depend on the viewing angle, so that where you see the fireball neutron stars. So this is the main result. And actually we can apply this to the observed population of Magnetar. Here I take, what I show is the famous flares, storm flare from this Magnetar. And there are actually, this is a light curve. So x-axis is time, y-axis is a photon count. So you see different morphology in light curve. And for these 3 flare, we take spectra independently and then try to fit. So this is the result. So blue is the original spectra, which cannot apparently explain the hard X-ray tail here. However, with the best fit parameter, we can beautifully explain the observation. Actually, the quality of the fit is extremely good. Reduced chi-square is close to 1. So this is a light curve. So this looks like different in light curve. But this is the very typical result. And what we can infer is the temperature of the fireball, original fireball temperature. So this is about 6 to 7 keV for this Magnetar first. And we can, of course, we know the distance to this Magnetar. So we can infer the size of this fireball, which is about 2 times the neutron star radius. So actually this is not very compact, but extended, but still kind of compact structure. So what we can see is that maybe the velocity distribution of the electron during the flare is likely non-relativistic. And also the single scattering of this process is enough to explain this kind of Magnetar flare spectrum. So this is the conclusion. Okay, so this is the summary of the first part. So the most important message is that inside Magnetar magnetosphere, we cannot avoid this scattering process. So this is the most important takeaway. And actually, we need to also apply this to different kind of Magnetar flare from different source with different energy. So this is a kind of ongoing work. So eventually, maybe we can kind of implement more parameter inside the model. Maybe like the angle between the magnetic field axis and also the rotation axis or magnetic field strength. So this is the first part. If you have questions, sure, please.
Could you go to the previous slide?
Yes.
So from the injection model to the observational process, and we can see the spectrum get harder.
Yes.
And assuming the harder should be gain the energy from the electron, but if the electron is not very energetic, not realistic, I don't understand why you make the emission spectrum harder in this way.
Oh, I mean, okay, sure. So this is basically the so scattering. So even if the electron is not relativistic, for example, if it's mildly relativistic, the Lorentz factor is less than 10. It is still enough to shift the energy of photon by a factor of few or 3. So this is the reason, answer to your question, I think.
I see.
So of course, normally electron is moving with much higher Lorentz factor when
Yeah.
magnetar flare is not occurring.
But my another question is the B field. Is the B field important here? I mean, because maybe you can still do the inverse Compton scattering to get the similar result, just by inverse Compton
Just
scattering.
the scattering process. Okay.
Yes.
No. I think in case of Thomson scattering,
Inverse Compton scattering, not Compton.
I know. So Thomson, right? So not a resonant one.
Yes.
I don't think so because it depends on the density of the electron population. So inverse Compton scattering determined by the number density.
Yes.
And of course, we don't know much about the number density, so it's hard to be modeled. But as I estimated, the inverse Compton scattering process is less dominant than this process. Also, second question: does this depend on the magnetic field? Answer is no. Why? This is because we only need a dipolar geometry, and actually this model doesn't depend on the surface magnetic field strength. So this is just because we know, for example, if we inject photon with this angle, we can uniquely determine the electron velocity. This is the reason. However, of course, the higher magnetic field maybe result in different scattering layer location. Location of the scattering depends on the magnetic field. And this scattering location must be much far from the star, because now we are kind of approximating this fireball structure as a point source. So depending on the magnetic field, this assumption might break. So maybe this could be maybe relevant, but not so important in my modeling. Yes. Thank you for the question. Sure. So maybe this is a bit kind of too specific research, but actually this is the first time to present this kind of a toy model for magnetar flare, and we succeed in the explaining the discrepancy between observation and the theory. So the next topic would be maybe less specific. So I talk about the connection, potential connection, how magnetar is different from radio pulsar population. So again, this is a kind of diagram. X-axis is the rotational energy loss. So this is the kind of rotational energy of the neutron star. And the y-axis is the surface X-ray luminosity. As you know, so there are so many populations, and the typical radio pulsar is around here. Typically, the rotation powered radio pulsar has higher rotational energy compared to the X-ray luminosity. This X-ray luminosity is supported by the magnetic energy. So this is consistent with the picture. Radio pulsar has relatively low magnetic field compared to magnetar. And here, of course, we have magnetar population. Actually, this bar shows the modulation of the magnetar flare luminosity, because they sometimes burst, sometimes not. So they have some modulation over time. So anyway, for this source, this surface X-ray luminosity exceeds the rotational energy. So this indicates a very high magnetic field. And actually, we have recently this kind of a population in between magnetar and a normal radio pulsar, which is discovered by radio observation. They have radio pulse, but eventually, after observing well, then we know this has relatively high magnetic field. And also, after watching this so many times for some period with gamma ray detector, we sometimes observe a flare from this population. So this population is actually the border of these maybe more distinct populations. So some magnetar behaves like radio pulsar occasionally, and also vice versa. So radio pulsar also sometimes flare in gamma ray or X-ray. So this is the current picture.
Excuse me.
Sure.
So I was wondering how we measure the rotational energy loss rate in this case.
In Magnetar.
Yes.
Yes, that's actually I mentioned in introduction, but let me repeat again. It's a very good question because we first observe, we know the location of Magnetar by bursting activity. Then we can have a pointing observation for some period. Then we can detect the pulsation of X-rays, not the radiation. Then this pulsation in X-ray reflects the rotation. So if we have enough observation time, we can determine the period and the period derivative for Magnetar as well.
Yeah, but that's maybe also associated with, maybe the inclination angles
Yes.
of the observation.
Of course, yes. So I think
The uncertainty.
uncertainty always exists. Yes. So of course. So actually, the uncertainty also exists in classical radio pulsar population, as you know. So it's not kind of established, but we use the same formula for many years because we don't know what's going on.
Yeah.
But anyway, these are different populations, but there is no clear boundary. So this is our observational kind of understanding of neutron star. So neutron star zoo is maybe continuous. So then it's very interesting to focus on the source around here, rather than looking at the extreme one, like here. So focusing on star around here is more interesting, and this is the motivation of this work. There's a very interesting observation almost 5 years ago by Canadian group. Actually, this is the simultaneous observation of, actually, I should say maybe highly radio pulsar. So this is very noisy, but this is a radio pulse from this pulsar. Okay. Then these people observe this also in X-ray. And then occasionally they detect Magnetar flare. Then 3 times Magnetar flare occur, and every time the radio flux is suppressed. And then it takes some time to recover to the normal radio pulsation radio flux level. So this is very interesting because the X-ray burst suppress the radio emission. So this may be related to the something, what's going on near the star. So this suppression time scale is roughly speaking 100 seconds. On the other hand, this star is rotating relatively fast, so 0.4 second rotational periodicity. So this time scale is much longer than this time scale. So this is not likely from the magnetospheric effect. So because this is much shorter, but this is much longer. So we need something to explain this. So I consider this kind of picture. So first, this is the very too simplistic picture of the radio emitting region of a neutron star. It's beamed, and we see every rotation. And when Magnetar flare occurs, maybe it's possible to have an expanding component of the fireball. We discussed before the confined fireball, but it's also possible to have the expanding component, and this component will, because this energy is so huge, so it has a high radiation pressure, so it will expand quickly, and this kind of a phenomenon is observed in solar flare. This is called coronal mass ejection. So actually in this case, this is the highly baryonic material, but we see the similar phenomena in stars. And eventually this fireball is covered the radio emitting region. And of course, if this plasma is dense enough, this can suppress the radio emission. Even though this radio emission process is continuing, we never observe. So this is the radio suppression process possible. Why do we see always the X-ray flare? Because X-ray flare is not affected by this plasma. So this might be the possible reason. So I try to explore this. So first, maybe So I should skip some material. So basically the magnetic energy is converted into creating fireball. So this fireball is expanded. While some energy is used to heat the surface of the neutron star, which create hot spot or confined fireball. Then this has, of course, black body emission. So this is also in X-ray. So this is how we see Magnetar flare. So this is some energetics, but I skip. This is not important. So the more important is how to hide radio emission. So there are many absorption processes in astrophysics, but here I consider the just simple plasma cut-off effect. So I think in cold non-magnetized plasma, we have this dispersion relation. This is the frequency of the wave, and this is the number of the wave, and also wave number, and this is the so-called plasma frequency. And the plasma frequency is just depending on the number density of the plasma. And if the radiation wave frequency is smaller than this plasma frequency, any wave can, no wave can transmit further. So this is kind of absorption process. So this happens. Originally, fireball number density is high enough, but eventually this number density decreases. Then plasma frequency changes as time goes. So this so when this is equal to the radio frequency, we observe in gigahertz typically. So then radio emission can be observed again. So until then, we have always this condition. So we never observe radio emission. So this is the process I consider. So this is very simple. Then, okay, so what we need to know is the number density evolution, how fireball plasma evolve as time goes. So this is actually done in the context of gamma ray burst. Gamma ray burst is also a high energetic burst of gamma ray from other objects. But typically we can solve the energy momentum conservation, and also we can conserve number of the particle. And then we have very simple formula. So this is the bulk Lorentz factor of the fireball. And if you this is proportional to the radius from the star. So if you travel 10 times, Lorentz factor is 10 times higher. So actually it accelerates because the radiation pressure, radiation energy is converted to the kinetic energy. So kinetic energy increases as time goes. And also the, okay. So, but there is a limit for this acceleration because we have limited number of radiation energy. So basically we can solve this equation analytically. So this is the schematic picture. Originally, the fireball is dominated by radiation energy because it includes so much gamma rays. However, after it expands a bit, this energy is converted into the kinetic energy, so the fireball becomes dominated by matter. And then fireball becomes optically thin to gamma ray, so gamma ray escapes. Right? So gamma ray energy is escaped. Then it reaches constant velocity. So after this, it doesn't accelerate. So this is the very schematic picture. Okay, this is the evolution of the plasma number density. Actually, this is the number density of electron positron, and this is the plasma frequency. We need to kind of consider plasma frequency. So this is the energy of the fireball, energy of the flare itself. So this determines the evolution uniquely. And the plasma frequency decreases like this. And then this is the frequency. So we observe in gigahertz frequency. So this reaches gigahertz around the time of around 100 seconds. Then it continues to decrease. Then we can observe radio emission only after this. So this is very useful formula connecting shut-off time scale of radio emission and the fireball energy. This is typically, so this is also frequency. So this is a typical number, and this could be applied to the detection of the radio suppression event, this event. Let's say that this is about 100 seconds. Then we can determine the fireball energy itself. This is about 10 to the 38 L. So this energy, part of this energy is converted to make the surface hotspot. So this is radiating X-rays, and this is observed as this short burst. So this is the so during this time we have our expanding fireball. So after this, radio emission is not affected. So this is very interesting because we have some implication. So this formula tells, of course, the fireball energy is related to the potentially related to the radio shut-off time scale. So not all X-ray emission is observed because the X-ray observation has some limit, right? So sensitivity limit. However, if we observe radio pulsation so long time and we identify when the radio flux decreases, then we can measure time of radio shut-off time scale. Then we can use this formula to infer the energy of the fireball. Actually, this fireball is not observed in X-ray. So in this way, maybe we can connect, only using radio observation, we can constrain the event rate of less energetic flare, which is not observed in X-ray. So this is the one possibility. A second possibility is more unique, I think more interesting, because we have a shut-off time scale depends on the frequency. So if we observe radio pulse with different frequency, then we can tell the difference. So this should satisfy this kind of relation. So higher frequency wave, higher frequency radio pulsation shut off earlier. So this is the test of this prediction. So this is maybe this is the summary of the part 2. So I don't have much time, so I need to quickly go to the section 3, and then I ask for questions. Actually, this is a bit different topic, so I'm not sure I have time, but let's try. Okay, so this is the topic of fast radio burst, which is different from the radio pulsation of magnet neutron star. So fast radio burst is actually discovered about maybe about 2007, so it's 15 years ago. And around this time, no one really is cosmological, maybe astrophysical origin. But after the discovery of few more bursts, then people try to think this is real. And actually, this is the spectrum, dynamic spectrum of fast radio burst. This is more easy to see. So we observe this kind of single pulse suddenly from high galactic latitude. So this is very peculiar because normally we see this kind of pulse from neutron star along the galactic plane. But if it comes above galactic plane, we suspect the cosmological origin. So it should be coming from much far distance outside our galaxy. So this is actually confirmed already by the discovery of 20 host galaxies of FRB at different redshift. And the galaxy types are different. And so this is kind of coming from the extragalactic place. And this is very bright, much brighter than radio emission from pulsar. And the duration is very short, millisecond scale, or even less. And it is so frequent, occurring maybe 1,000 times per day. And yeah, so this is the very interesting radio pulse. And intriguingly, some FRB, roughly speaking, so small fraction that they repeat multiple times, but without any periodicity. So repeat, like this sporadic behavior. But most of them is not observed to repeat. So maybe there could be some multiple population of fast radio bursts, which is unknown. However, people discuss often the origin of asteroidal burst could be related to neutron star, or maybe neutron star with strong magnetic field, namely Magnetar. This possibility has been intensively discussed so far. So that's why I talk about this. And this is how FRB could be produced. So this is a bit tricky, and it's still controversial, but we have, roughly speaking, two types of model. This model, I talk about this because this is maybe more close to pulsar emission mechanism. So along the magnetic field of the neutron star, bunch of particle is moving relativistic speed, and it will create radio emission at single frequency with curvature radiation. So this is the kind of emission mechanism happening near neutron star. And this model, so-called synchrotron laser model, is happening very far from the neutron star. So this is the occurring when neutron star maybe Magnetar flares, then some material is ejected, like fireball plasma. Then this plasma will interact with the interstellar medium or previously ejected material. Then this creates a shock. And this shock will create synchrotron radiation through the maser instability. So this is very very complicated process. So this is the other possibility. So these two possibilities are discussed, and this is why people are interested also in Magnetar and a neutron star when studying asteroidal burst. Then so this is the kind of so important observation in almost 2 years ago, April. So we actually detect asteroidal burst from this Magnetar. So this is a galactic Magnetar, this is galactic center, and this Magnetar is rotating 3 seconds, and this is very typical for Magnetar. Distance is just 10 kiloparsec, so galactic scale. And this Magnetar was becoming very active in X-ray when asteroidal burst was discovered. And so we detect simultaneously this FRB-like event with Magnetar flare. So this is the FRB signal. So they have 2 detectors at different frequencies, and this is stellar too, so forth. This is also chime. Chime was, of course, partly led by Willy Penn, the director, and also Shushan is involved. And so this is the pulse. The appearance of the pulse looks different, but this occurs exactly the same time. However, this is slightly different from normal FRB. Why? Because energy is much lower than typical FRB. The energy of the radio pulse energy is about 10 to the 35 L, assuming 10 kiloparsec distance. So this is the luminosity, and this is the duration. We plot many transients, like gamma rays, supernovae, some other stellar emission. This is a typical pulsar radio emission. So this is about this energy luminosity level. And this is a typical FRB from cosmological distance. This is super bright, 10 to the 33. However, this event is in between these two, around here. So this is still closer to FRB. This is, of course, the faintest FRB, if this is FRB. So most people think this is the extension of this FRB population. Luminosity function actually, roughly speaking, match this FRB is here, and this is the typical cosmological FRB, which is much brighter. But maybe this is connected by typical luminosity power law function. So I say, so this is FRB, but galactic FRB, the first one. And what is special about this FRB? This is the FRB emission, and this is the X-ray observation. And almost around the same time, we also detect hard red X-ray burst by several instruments. This is an integral, and actually they have some spikes here. And these spikes are, roughly speaking, consistent with FRB emission time. So these two are actually related. So this is the first confirmation of FRB-like emission from actual magnetar. So maybe this is the milestone to step forward to understand FRB. So I want to talk about what kind of process, what kind of plasma can explain these two X-ray and radio observation. So this is the purpose of the last talk. So I'm not sure I can finish, but okay. So let me try. So next, this is not a radio observation, but the X-ray observation of this event. Actually, this event is also very weird in X-ray observation because typical Magnetar flare is having this flare have the similar flux level compared to typical Magnetar flare from the same source. However, only this event have much higher peak energy. So it is above maybe around 80 keV. The peak of the spectra is much higher. This means this is much harder event, more energetic event. So this spectrum is completely different from typical population. So something weird is going on. So this is also something peculiar about this FRB event. So we need to solve both this peculiar X-ray event and the past radio burst event. So I summarize the arrival time of radio FRB, this is the FRB, and this is the X-ray burst. Because they have two peaks, this has only one peak in radio, but please forget it. So radio and X-ray observation have some relatively accurate arrival time measurement. And actually, if we can tell there is some time difference between radio observation and X-ray observation, this kind of time difference limits the distance from the neutron star where this event is created. So this time difference is at most 10 milliseconds. So this means if we consider outflow with some Lorentz factor, gamma, then the location of this emitting region is less than this value. So gamma squared is the relativistic effect, and the c is the speed of light. This is the time difference of arrival time between X-ray and radio observation. So we can, roughly speaking, constrain the location where FRB is produced. So next. Okay. So next, we need to think about the spectrum of the hard X-ray flare. So this is the observed flare spectrum. This is energy. And okay, so this is the model I introduced in the first section of this talk. So this is my model on the Magnetar flare spectra. If this is normal Magnetar flare, this is okay to explain the observation. However, we still see here, this is much harder, right? So we have a non-thermal component. So this component cannot be explained by the trapped fireball origin, fireball connected to the neutron star. This is not enough. So we suspect this non-thermal component is coming from the outflow material, outflow plasma. So this can maybe produce this kind of hard X-ray spike. So the global picture could be like this. At the time of Magnetar flare, of course, fireball is created, and this is emitting thermal X-ray emission. However, somehow outflow is also produced. Then some process here will create both radio emission and also non-thermal component of the X-ray. So what we see in X-ray observation is that just a superposition of this and this. So maybe this could give some implication. So of course we don't know what kind of energy dissipation happens here, and we want to know the distance where this happens, and also we want to know what kind of outflow can produce this. So this is the purpose. I should skip some slide. So I first constrain the trapped fireball quantity. So by some analysis, we can actually constrain the temperature of the fireball and the fireball size. So the energy of the fireball we can constrain. And so we can constrain the fireball quantity. this is typical gamma ray energy, and the size is 10% of neutron star radii. So this is produced when likely produced when the flare happens. Then next, we want to constrain this property, outflow property. This is a bit more complicated, but we consider three possibilities. So because we don't know the property of the outflow, outflow could be purely leptonic, consisting of only electron positron population, or of course it could contain protons because the magnetar of course have protons on the surface. So it's possible. So some baryonic outflow is possible, and more of course magnetic outflow is also possible. So magnetic energy will accelerate the plasma. This is also possible. So for three possibilities, we use the analytic, maybe simplistic model to track the evolution of the fireball, like I do in the previous section. So this evolution only depends on the initial property of the fireball. So we know the initial condition already from the constraint on the trapped fireball. So then we can constrain the outflow property from observation. So that's same as the previous section, we consider plasma cutoff effect. Of course, this is a bit more different when you consider laser emission, but I skip this. So this is basically similar to the plasma shutoff effect. And also, we already mentioned the position of the emission is constrained by the time difference between the X-ray and radio observation. The next one, there's also compactness limit. So this is very famous in gamma ray burst, but because we observe very hard gamma rays, tip is very hard, very high energy. So this means the environment of the plasma should be optically thin to Thomson scattering. So this means there is a lower limit on the radius, above which X-ray emission is escaped. So this is very simple argument. So this sets some lower limit on the X-ray radiation. The final condition could be, this is not so clear, of course, but because the X-ray emission is so bright, so if this is happening through some kind of synchrotron process, the cooling time must be faster than the dynamical time. Otherwise, the emission is not so strong. So this kind of condition could be combined to constrain where this emission occur. So I talk about the pure electronic case, only electron-positron plasma. So this is similar evolution of the number density. This is plasma frequency. And we can constrain the location where X-ray is produced and the radio is produced. Actually, you can see that these two regions is not overlapping in this case. So this indicates, actually this model is not likely. So I skip some, okay. So this is a baryonic case. So if there is a proton, also proton is included in the outflow, then we have maybe slightly better condition. Sorry, this is very difficult to see, but I tried two different parameters for baryon, how much baryon there is a baryon. So this is the less baryonic case. This is highly baryonic case. And we have some overlapping region around here. And the time scale of radio emission is also consistent with FRB, around 1 millisecond to 100 milliseconds. So maybe this kind of condition may, because this model depends on data, this parameter, so we can in turn constrain this parameter. So this tells you that some upper limit on the baryon load. So you cannot have too much baryon inside the plasma. Otherwise, we don't explain two observations. So this is the first case. I skipped the magnetic case because it's similar. In magnetic case, this is the initial magnetic, how the plasma is magnetized. So highly baryonic, highly magnetized case can also have similar result, which could be consistent with observation. So in this way, okay, this is the conclusion. Maybe I shouldn't skip. Yeah. Okay. So So basically, we have so many things going on here. But we can constrain the outflow property by this kind of modeling in general. This is very general analysis. And we need some special condition for these events to happen. Because some condition, how much proton is inside the outflow, and also that it should be maybe some highly magnetized. Non-magnetized outflow is not enough to explain both. So this kind of condition constrains the outflow. And this tells you the parameter should be highly fine-tuned. Otherwise, you cannot explain this observation. So this means maybe FRB event associated with this kind of X-ray burst is not common. This is very, very rare because of the requirement of this fine-tuning. This is the implication. Of course, we are not 100% sure about what's going on because we neglect some, maybe we may miss some physics. However, this is very general analysis. And also, finally, lastly, the constraint on the value material we obtain is around this value, less than 10 to the 14 gram. Actually, in the past observation of the gamma ray Magnetar flare, there is a constraint from the radio afterglow observation. This is actually much larger amount of mass. So in this case, so comparing these two, we can tell this event have much less baryonic material compared to the giant flare. It is very reasonable because giant flare is more energetic, so maybe it could contain more material from the star. So this is the implication and the conclusion. So the final takeaway is that I focus on the hair plasma in this talk, and actually this is very maybe inevitable when you consider how this kind of bright radio emission on so that hard X-ray emission is produced from Magnetar. So maybe this could be more important in the coming years. Thank you for listening. That's all.
Okay, we are actually a little bit out of time.
Yeah.
Do we have one or two quick questions? Okay.
So, thanks for a very interesting talk and enjoy. And there's one quick question I want to ask is about the physical mechanism for the fireball itself. Because all these analyses were relevant to the property of the fireball, which you didn't mention too much about the fireball itself.
Yes.
So what do you assume to generate the fireball in the models?
Okay. Yeah. It's I think it's one of the fundamental question, which is very important actually. However, this process is not well known, so people often skip this process. So of course, so it's very simple. So just injecting pure energy to make some electron positron gamma ray population. So this is likely because the surface magnetic field is so strong, so 10 to the 14 Gauss, and so this magnetic field will interact with gamma ray, and this create pair, electron-positron pair, and these electron-positron pair also are annihilate to create the gamma ray population. So this kind of cascading phenomena is happening within very short time scale. Then it is likely to form this kind of population. So I think there are maybe 3 or 4 cascading process of creating this population. However, we are not able to calculate how this happens within such short time. And actually, we don't know where the magnetic energy is injected. We don't know. It could be inside a magnetosphere or from the star surface. So this is also a still unresolved problem. So
here, mainly the energy source was from the magnetic field.
Magnetic field.
Maybe by the reconnection process,
yes.
or other, or maybe some people talk about earthquake, the crack of the crust of the neutron star.
Exactly. So
Yeah.
that's also what I didn't talk about. Sometimes neutron star itself has a star quake, which is caused because neutron star surface is a crust, which is very dense, kind of crust region of 1 kilometer distance. And this crust has sometimes crack, and this crack is going back to the original. So how to say? It's difficult in English, but so anyway, this kind of activity trigger star quake, which is the source, could be the source of energy injection from the magnetar itself. Yes, exactly.
Thank you very much.
Yes. So this is also interesting, but people stop to think about it after 2000.
Yeah.
Yes. Only we have classics here.
And also in your X-ray observation, you show the 3 of these peaks or curves. And I was wondering, this flare fireball event usually, what's the frequency for these events?
You mean the X-ray event?
X-ray.
X-ray
burst.
X-ray burst. Okay. X-ray burst energy range is between maybe around 10 keV up to gamma ray range, like MeV. So this is a typical range of the energy, but mostly coming from hard X-ray or soft X-ray. Maybe 10 keV is very typical photon energy we observe.
So how frequent they occur?
It's an interesting question. Actually, it highly depends on the source. However, we have a tendency when magnetar becomes active, it creates forest of burst. During some maybe for 3 months or maybe even half a year, then it stops the activity. So this kind of very sporadic activity is observed. But a very low energy burst is very frequently observed during this period. So during the activation period of neutron star, we see so many flares. The lowest energy flare is observed so often. Like I showed once, you can see the first flare here. Just a moment. Sorry. Here. So you can see this time scale. This is the second time scale. So during 10 seconds, we have so many energetic flares. So this is the case when it is activated. Yes.
Thank you. Thank you very much.
Thank you.
Any other questions? Then if not, let's thank Shotaro again.
Thank you.